friends, welcome to continue following up this channel. So in this video, I'm going to analyze problem 863, all nodes distance key in binary tree. So our main strategy for this problem is that we review this problem as a general graph problem, and then we use traversal to address it. So in the previous video, we analyzed problem 2385. Actually, the same idea or almost identical codes can apply here, right? So our plan will be the following. First, we're going to digest the problem requirements, and then we do a simple analysis, and then we look at the coding. So during the coding, we are going to make some comments to help you understand this problem and also related problems. So with that said, let's look at the digest. So here we are given the root of a binary tree. In other words, we are given a binary tree data structure. So also we are given the value of a target node called target and an integer key. So we want to return an array of the values of all nodes that have a distance key from the target node. And we can return the answer in any order, right? So this is the one, still we are given two examples. And the second example is very special, right? So you can regard it as an edge case. And also, I want to first look at the constraints in this problem. First, the number of nodes in the tree is in this range. So the maximum number of nodes is 500. In other words, this problem is a small size problem. And the node values are in the range 0 and 500, the closed interval bounded by these two numbers. And all the values are unique. So this is a very key assumption. So this assumption is the same as problem 2385, right? And target is the value of one of the nodes in the tree. In other words, this is again a consistency assumption. And here k is in between 0 and 1000, right? So if the k is too large, because the number node is at most 500. So for example, it's greater than k is greater than 500, and then we are going to return empty, right? So that's just a very simple observation. So the key point or the viewpoint for this problem is that we don't work on the binary tree. Do not directly work on the binary tree, right? Or rather, we will this as a general graph problem. So once you have this point, and then the problem is solved, right? So then the target is nothing but the source. And then we can do breadth first traversal. For example, the nodes 3, 0. So here, let's see, target is 5, right? So the target is 5. And then the nodes 3, 2, and 6 is one distance from 5. And then we look at C1. So this is distance 2, right? And 7 and 4 is distance 2. And then if you look at 0 and 8 is distance 3 from 5. So this way, we just need to do a breadth first based traversal from the source given by the target. And then we just record the distance, right? So the distance actually corresponding to minutes in problem 2385. So with that said, again, we are going to do two traversals. In the first traversal, we're going to build a bidirectional graph, or we can call it undirected graph. This is the first one. So once we build the graph, we can do traversal with source 5, say, our target, and then the distance is 0, right? Then we just expand layer by layer outside. So once the layer number is equal to k, right? And then we're going to return the corresponding nodes values. So with that said, let's do the process. So here I'm going to write f. F means build a graph. So this is just for the ease of writing. So we have a root. So here I'm going to do traversal. So as we mentioned, any traversal will do. So here the thing is not the what specific traversal algorithm you use, but the idea to build the undirected graph. So here I'm going to get graph as collections default dict. So I'm going to put a callable here as a set. You can regard this as a function, or you can see if by default we map anything to an empty set, right? So this actually help us avoid do some key checkings when we want to access elements in the dictionary. So this is one thing. And also, in this problem, it's assumed that the nodes is at least 1. But for completeness, if not root, so I'm going to return the graph state. In other words, an empty graph. So this is just for building the graph purpose, or just to make it complete. So if you use a recursive format of this traversal, you can see this is the base case. But here I want to use iterative format just to help you understand the details. And then I'm going to use depth first based traversal. Here I'm going to, because now after this if block, root is not null, so I can put it in a stack. And then I'll do the standard or routine traversal while loop, right? So node, so it's stack pop, right? Then I'm going to check if the root has children's, right? So if node left, then we see that there's a bidirectional edge between node and its left subtree. So we're going to build these two edges, or one unidirectional edges, and then add the node left to the stack. So this is very straightforward, right? We have node, so we can use value rather than use tree nodes, because if we use value, we just save a number, right? Without saving its subtrees. The reason we can do this is due to the assumption that all the values are unique, right? Then this is a dictionary, this is a set, right? We can add node left value. So it basically says that node left is a neighbor of node. In the opposite direction, we see that node left, node is also a neighbor of node. Node left is also neighbor of node itself, right? So node value. So once we done this, so we can stack append node. So here we need to add node. The reason is that we want to check the subtrees, right? So the node should be a tree node object. So this is left. Similarly, we can do right, right? Let's copy this part. I just make some modifications. I change this left to be right, right? So here, right, I think it's enough. So once we've done this, so we are going to modify the graph. Then we just need to return its final state, right? So notice that graph is a subclass of dictionary, right? So it's default dictionary. So with that said, we can first do a check, right? So the f root. So for example 1, we know the dictionary. It's running slow. Let's see. Anyway, time limited. Let's see. Stack pop left. So yeah, we need to add a node left. So here node right. Now let's test. Yeah. So here we know 3 has neighbors 5 and 1, and 5 have neighbors 3, 2, 6. That's 3, 2, 6, and 1 has neighbors 3, 0, 8. Right? 0 is a leaf, it has a neighbor 1. 8 is a leaf, it has neighbor 1. And 6 has neighbor 5, and 2 have neighbor 5, 7, 4. And 7, 4 both have neighbor 2, right? This is right. So now we are ready to, let's first get graph. Let's see, graph equals f root. Make it ready. So now we are going to do traversals, right? So the source will be, let's see, the target. So notice that the target is a tree node. We want to retrieve its value, right? So because in this graph, we used integer values to represent nodes. So the source and with itself has distance 0, right? Basically, we choose node and its distance to target, right? You can see to target value or anything, but you need to be aware. So here we are working with integer numbers, but we use them to represent nodes. So we have this graph, and then let me initialize a result variable to hold the return. So this is the source. I'm going to use a queue. So let's use DAG, but we just use a queue behavior. So add source to it. And then I also need a dictionary, like visited in the previous problem. So we just use this one to avoid repetition, right? So with this done, with this preparation done, so it's a standard while loop, right, for breadth first based traversal. So here, let's first get the node and the distance. So we're going to say q pop left. And then we are going to check if node not in sim. So we can first add it to the visited, or we can first check if distance equals k. Let's see if distance equals k. So we're going to say result append node. So here node is an integer value, right? So no matter if this holds or not, we need to do sim add this node, right? So next we are going to look at the neighbor of this node. So it's for neighbor in graph node, right? So let's check if neighbor not in sim, right? So we are going to append this guy to the queue. So this is the neighbor, and its distance is distance plus 1 to the target, right? And then after we do the traversal layer by layer, and then you can return the result, right? You can understand the breadth first based traversal as radiate layer by layer outside this source, right? The first layer 3, 2, 6, the second layer 1, 7, 4, the third layer 0, 8, right? So with that said, basically this forms a solution format to this problem. So now let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So that's basically about it for the analytic parts for this problem. Let's make some comments so that you can generalize this idea. So sometimes, when we work on binary trees, so we have lots of traversal algorithms like in-order traversal, pre-order traversal, post-order traversal, zigzag traversal, level order traversal, and so on. So for this problem, we're using the binary tree traversal to build the graph. So here, the tree, if we fix a node, and due to the relation of children and parents, it's sort of directed. And here, because the problem requirement, we build a undirected graph, or say bidirected graph. So that's the thing. But in the process of building the graph, so as to what kind of specific traversal algorithm, it does not matter, right? So once you've done that, so you can do another traversal. So this time we work on a general graph, and then we do breadth first based traversal to select those values which are key distance to the target. So in this problem, we are using the target value as the source, right? And then we do traversal. So basically that's the comment for this problem. But if you compare the code for this problem 863 with the code for 2385, so they are almost identical, right? So that's what we basically want to demonstrate. So you can use same idea to solve a class of problems. That will be very beneficial. Or you can solve a same problem using different formats of different ideas. That's also beneficial. So with that said, I guess that's it for this current video. If you're interested, you can follow up. We're going to do a simple one It's still a related problem to today's daily challenge problem 2385. With that said, thank you.